Okay, so we get a time constant of a millisecond, right? So time constant is 1 millisecond, very straightforward calculation, okay? And this is observable. With available equipment, okay? Available instruments, I should say instrumentation, but what the heck, okay? And what you then get is, okay, if you have some initial current, it drops off like this, okay? 1 over E I naught would be about here. That's about 0.37 of that, meaning that this is your L over R. Okay? And then you go another L over R, and you're down to 37% of that, which is about a little over 1/10 of what you started with. Okay? 15%, 1/6. Okay? So there's your picture. You know, that's what happens. Okay? That could be observable. If your resistance is on this order and your inductance is on this order. So the question is, what's the inductance of 60 loops? Okay? Of radius 9 inches, 25 centimeters, 23 centimeters, whatever, okay? So what you have to do now is you have to figure out what the magnetic field is if you have a given current in just one loop of that. Then you multiply that by the number of loops, 60 of them, okay? That gives you the magnetic field at the center of the coil. Then you take into account that this is wrapped around iron, so you probably get on the order of 10 times that magnetic field. Right? And then, of course, you take the data you have in lab that relates the magnetic field that you measured to the current. Okay? And you didn't do it for that particular setup, but you did it for the small coil, with and without the iron bolt in the middle, okay? So you kind of know that, so you know all that from lab, okay? And that allows you to calculate the inductance. If you know the magnetic field as a function of the current, then you can find the inductance as a function of the current. Then you can ask yourself, well, how does that scale up for this big thing, okay? So that's what we want to do.